Hello and welcome. Today, we are pulling back the curtain on what is, without a doubt, the most fundamental piece of technology in all of computing, the algorithm. Seriously, from the phone in your pocket to the International Space Station, everything, and I mean everything, runs on these incredible, invisible engines. All right, let's jump right in. It really all starts with this one simple question. We ask computers to do all sorts of amazing things, right? Sort our family photos, find the quickest route to work, you name it. But how do they actually go from being given a problem to spitting out a solution? Well, the answer, in one single word, is algorithms. So, what exactly is an algorithm? The best way to think about it, and the way it really clicks for most people, is to think of it as a recipe. It's the step-by-step set of instructions that tells a computer precisely what to do to get from point A to point B. Now, the formal definition can sound a little technical, but that cooking recipe analogy, it's perfect. You have your ingredients, that's your input. You follow a very clear, finite sequence of steps, that's the process, and at the end, you get a finished dish, and that's your output. The key things here are that the steps have to be totally unambiguous. And, crucially, they must eventually end. You can't have a recipe that goes on forever. And make no mistake, this is not just some abstract academic concept. Algorithms are the absolute core technology, driving pretty much everything in our digital world. The way data gets compressed so you can stream this explainer without it buffering every 5 seconds, that's an algorithm. The way a network routes that data halfway around the world to you in milliseconds, that's an algorithm. The way a search engine finds that one specific piece of information in a digital haystack the size of a galaxy, you guessed it, all powered by algorithms working tirelessly behind the scenes. Okay, so knowing what an algorithm is one thing. But how do engineers actually, create one? It's definitely not magic. It's a really rigorous design process, kind of like an architect drafting a detailed blueprint long before anyone starts pouring concrete. It always starts with deeply, truly understanding the problem you're trying to solve. From there, you'll pick an approach, you'll detail every single step, analyze how well it's likely to perform, and this is probably the most critical step of all, you have to prove that it actually works. Not just sometimes, but every single time. This quote just gets right to the heart of it, doesn't it? It explains exactly why that last step, proving correctness, is so important. In engineering, mostly right is the same as wrong. I mean, think about it. An algorithm for a heart pacemaker or for a plane's flight control system, it can't just work sometimes. It has to be perfectly reliable, and it has to finish its job. Correctness is everything. And getting that correctness means you have to be on the lookout for all these common traps. You have to ask yourself, does my loop have a guaranteed way to exit, or could it run forever? Am I off by 1 in my calculations? That's a classic bug. A great algorithm doesn't just work for the average case, it has to handle all the weird edge cases too, like what happens if you give it an empty list or a list with a billion items. So now let's open up the engineer's toolkit. When a good engineer is faced with a problem, they don't just start typing code randomly. No, they reach for a whole set of proven problem-solving strategies to find the absolute right tool for the job. Let's look at 2 really fundamental strategies here. On the one hand, you've got brute force. It's simple, right? Just try every single possibility until you stumble upon the answer. And hey, it'll get you there eventually, but it can be incredibly slow. But then, on the other hand, you have something elegant, like divide and conquer. This is where you cleverly break a huge problem down into smaller, much more manageable pieces, solve those little pieces, and then stitch the results back together. It's often worlds more efficient. And believe me, that toolkit is deep. You've got greedy algorithms, which are all about making the best possible choice for right now, hoping it leads to a great overall solution. Then there's dynamic programming, which is super clever. It remembers the answers to things it's already solved, so it doesn't have to do the same work twice. And sometimes, when a perfect solution would take forever to find, a heuristic can get you a good enough answer really fast. Choosing the right strategy is a huge part of being a great engineer. Okay, so you've designed a correct algorithm. You used a really smart strategy. Fantastic. But how do you know if it's any good? How do we measure its performance in a way that everyone can understand and compare? For that, we use something called Big O notation. Think of it like a universal report card. It gives your algorithm a grade that describes how its runtime scales as the size of the input, which we call n, gets bigger. So something that's O of n, or linear, means if you double the input, you pretty much double the time. But something that's O of n squared, or quadratic, well, that gets slow much, much faster. And this is where you can really see the mind-blowing difference. A linear algorithm scales gracefully, a quadratic one, it starts to struggle as the input grows. But an exponential algorithm, O of 2 to the n, it becomes completely useless almost immediately. To put that in perspective, searching for a name in a phone book of a billion people with a linear algorithm could take days. A logarithmic algorithm could find it in about 30 steps. That is the difference between possible and literally impossible. So let's bring all of this together. We've talked about what algorithms are, how they're designed, and how we measure them. But why does any of this really matter to you as an aspiring engineer, as a problem solver?
It matters because every single time you write a function or a loop or any piece of code, you are designing and implementing an algorithm, whether you realize it or not. Understanding these principles is what separates someone who just writes code from a true software engineer, someone who can build solutions that are not only correct, but also elegant, efficient, and can scale to solve massive problems. At the end of the day, algorithms are the language we use to teach machines how to solve our problems. They are the true engine of the modern world. So, the only real question left is this: what problem will you design an algorithm to solve? Thanks for watching.